So now we're going to look at the parameter a, and a is a constant multiplied by the relevant trig ratio. So I'm just going to consider the trig ratios a sine theta and a tan theta. A cos theta I'd like you to verify on your own. Okay, so let's get some values for theta. 0, 90, 180, 360. So remember, when our range goes from 0 to 360 degrees, we're capturing one full sine wave. Okay, let's have the function sine of theta. So for sine of theta, the value of a is 1. Okay, our values are 0, 1, 0, minus 1. And for 2 sine theta, all we're doing is multiplying these function values by 2. Okay, so we would plug in 0, get sine of 0, and times it by 2. We plug in 90 degrees, sine of 90, and times it by 2. So I'm just going to times everything here by 2. So 2 times 0 is 0. 2 times 1 is 2. 0 minus 2. So let's plot this and see how this parameter affects our standard graph. Okay, our maximum is 1, our minimum is minus 1. I'll make it 2 and minus 2 because of this graph, and then in between is going to be minus 1 and 1. So I'm going to plot the first one, sine of theta. So we get a sine wave like this. And now for this graph, which I'm going to draw in purple. Let's make this black. So for this graph, all of the y values are being doubled. So for 90 degrees, we'll get 2, 0, negative 2, and back to 0. So this graph has higher peaks and lower troughs. So basically it's just stretching out the y values. So now let's see how the parameter a affects the tan ratio. So similarly to the sine ratio, we expect the parameter a to stretch out the y values. So let's see how this works. Once again, I'm going to use our standard graph tan of theta, and the value of a is 1, and I'm going to compare it to the graph 2 tan theta. So a larger parameter of a for 2 tan theta would theoretically stretch out the y values. So let's see how this looks. I'm going to pick some values for theta. Let's go 0, and we'll go up in 45s once again. Okay, all the way up to 360. So I'm going to plug the values in. So 45 is going to be 1, undefined, vertical asymptote, minus 1, 0, 1, undefined, negative 1, and 0. So once again, when we have this 2 times tan theta, all we're going to be doing is multiplying the y values by 2. So I'm going to do that for each of these. Okay, now let's plot these graphs and see. Okay, so 45. 90, 135, 180, 225, 270. Okay, so remember we use these increments of 45 because tan gives us 1 and minus 1. I'm just going to put in my asymptotes, 90 and 270. So this branch goes up like this. This will go like this. And this will do something like this. Okay, so I'm going to use our key. The first standard graph is going to be in black, and our changed graph is going to be in purple. So all our y values double, so I'm going to add two new vertical values, 2 and minus 2. Okay, so this one would go, let me just extend this. So this first branch would go like this, and then we've got -2, 0, 2. This branch will do something like this. And here we have -2 again. So this branch goes like this. Okay, so we can see that the y values have been stretched outwards in each case. So this should remind you of the hyperbola when we had parameter a and we saw how each of the branches became more bowed inwards or outwards towards the origin. So the same thing is happening here. When a has increased, it gets more bowed outwards away from the asymptotes. Okay, now let's move on to parameter q. So parameter q works in much the same way as it did when we were looking at the previous graphs, the hyperbola, exponential, and parabola. So basically when we have a plus q next to our function, it means that our y values are either going to shift up or down. So our y values will all shift up if q is positive, so we're adding to the y values, and our graph will shift down if q is negative. So I've summarized this here. Q greater than 0 means an upward shift of the graph, or correspondingly a downward shift of the horizontal axis. So let's just check that quickly. So if this is our original sine graph and q is positive, then our entire graph shifts upwards because all our y values shift upwards. Or you could think of it as our original axis sitting somewhere here. So our original horizontal axis was at this dotted line, and we moved it downwards, and this is our new horizontal axis. So essentially it made it like the graph shifted upwards. Okay, similar kind of idea holds for q less than 0. That will decrease the y values and lead to a downward shift of the graph. And if we move the axis, or the horizontal axis up, it also means like the graph has shifted down. So let's look at an example with some numerical values. So in the textbook, they look at parameter q for the cos function, and they show how the cos graph shifts up and down. The example I'm going to do now is for the sine function. So verify the cos function on your own. Okay, so I'm going to start off with our standard graph, sine of theta, and then I'm going to have an upward shift of the graph of +2 and a downward shift of the graph of -1. Let's put some values for theta. So once again, we'll just go up in 90s. Okay, let's solve. Sine of 0 is 0, 90 is 1. Okay, so for the the values of this function, it's going to be the same as the values for sine of theta, we're just adding 2. So I'm going to add 2 to each of these values. Okay, and similarly for the last function, it's all of these y values, and we're just minusing 1. -1, it's -2, -1. Okay, so now let's plot. Okay, my key for the standard graph is going to be a solid black line. For the upward shift, a line with some crosses, and the downward shift is going to be a purple line. Okay, now remember for our vertical intervals, our lowest is going to be -2 and our highest is going to be 3. So when you're drawing it, make sure you just have enough space. So -1, -2, and 1, 2, 3. Okay, so we're going 90, 180, 270, 360. Okay, so now let's plug and play. So for the first standard graph, 1, so it would look something like this. Okay, notice that it's a little bit flat here because my interval is fairly wide, so it stretches it out a bit. So now let's move on to our upward shift. So we've got 0 and 2, 90 and 3, then we go back to 2, then 1, and back to 2. Okay, so this graph looks something like this. And lastly, we have the downward shift. So just notice the upward shift moved the whole graph up, or you could think of it as there was an imaginary horizontal axis here and we moved it 2 down. Okay, so the purple graph is going to be 1 less than the original. And it looks like this. Okay, so that covers that for the parameter Q. I'm also not going to do it for the tan ratio. It works in a very similar way. Everything just moves up or down. So as a little exercise in addition to the homework that I've given you, I would suggest trying to do these little plots on your own, just to get really comfortable with drawing the graphs and getting the curves nice and even. So yeah, that concludes today's video lesson. I hope it was clear, and thanks for watching. See you soon.